All right. So, hello everyone. My name is Srinivasan Iyengar. I'm a fifth year PhD student and I'm working under Professor Prashant Shenoy. And my work is primarily in the area of cyber physical systems with a focus on smart buildings and smart grids. And possibly after this lecture, you'll know some part of what area I'm working on. So today's talk is about pervasive computing, IoT, and smart buildings. So computing is becoming increasingly ubiquitous, right from smartphones that we all possess to sensors that are all around us. And further, these mobile phones are becoming increasingly powerful. Each one of us has a smartphone which has around minimum of 10 to 15 sensors or more with more advanced mobiles. And also, we see that these sensors are part of our physical environments. They are in buildings, as I mentioned earlier, my smartwatch, this has a lot of sensors embedded in it. And this enables many new application domains. For example, in case of smart health, where a Fitbit tracker can not only track your activities, such as when you're walking, when you're swimming, but it can also keep count of your steps or the calories that you consume, and more importantly, the heart rate. Another application domain is smart buildings, where we see that there are Nest thermostats which can learn occupancy schedules based on machine learning algorithms and occupancy sensors that are present in homes. In fact, I'm very sure that this room itself has some PIR sensors which is looking at any motion, and possibly the lights would turn on whenever someone enters the room. Another area is smart transportation. We have all heard about Google's self-driving cars. There is another concept called connected cars, where one car can communicate with another car, and that can lead to many energy efficiency benefits, which I'll be briefly discussing in this slide itself. And finally, smart agriculture, where we have seen that people are using drones to monitor the moisture content of the soil. On the ground, there are pH sensor which continuously monitor the health of the soil. And all these things can have led to increased yield. So there are significant benefits, and we have already seen all these deployments part of our lives. Now, there are a couple of major drivers which have led to this rise in proliferation of pervasive computing. The first one is miniaturization of computing. So for example, there are tiny sensors with computing and communication capability. For example, you would have possibly, I don't know if you know this, but this term is often used. It's called MEMS, that is micro electromechanical systems. This is a slightly complicated name, but it essentially means that any sensor essentially converts some kind of mechanical motion, piezoelectric effect, magnetic effect into some form of electrical signal. Electrical signal can be change in voltage or change in current, and that change in current or voltage can then be further interpreted as recording amount of carbon monoxide in this room or some other measure. And expectation is that in the future there will be a Moore's law like growth in MEMS, in the sense it won't remain micro electromechanical systems, they will become nano electromechanical systems. So currently these sensors, which are classified as micro electromechanical systems, are in the range of 1 micron to 100 micron. There will be orders of magnitude improvement in the size of these sensors. And also, we have all heard this buzz term called IoT, this Internet of Things. This essentially means that all our physical devices now have the capability of exchanging messages among each other. For example, occupancy sensor can convey message to a Nest thermostat that there is nobody in the home. Possibly we can turn off the air conditioning unit. And there are many other applications which involve more than just two devices communicating. Any modern industrial plant will have thousands of sensors which are communicating with each other through what they call machine-to-machine communication. they might use some low power communication systems such as Bluetooth or Zigbee. There are different protocols. And now let me focus on one of the important application domains, that is smart health. Now, early wearable devices that you and I have and many of you would have do basic activity tracking. They monitor your sleep, your heart rate, and many other things. But there are new technologies which can do a lot more things. For example, to know how many steps you have walked, you need to always carry this the smartwatch with you. I don't know about you, but for me it is a bit invasive, and maybe this is not for everyone, right? So imagine your clothes that you're wearing already recording all this information which are already tracked by these wearables. And this is already happening right now. So there are these smart gloves or smart shoes. They can also use to detect sweat, which is used to detect anxiety in some drug addicts and also normal people who are working in an IT environment. So there are a lot of cool applications of all these sensors. Also, in fact, in UMass itself, we have this project called Smart Glasses, where you can have this a glass thing, a spectacle which is equipped with a camera, and that can actually track the gaze. That is how your eyes are moving while watching a computer screen. And this is used in fatigue detection. Also, there is, I think, a contact lens from Apple which can detect your blood sugar level. So there are quite a few applications of smart health. When it comes to buildings, currently all buildings are filled with a lot of smart devices. I already talked about a Nest thermostat, which is what Nest calls a learning thermostat. It can look at past occupancy pattern and learn a schedule of when you leave the house, when you sleep, and basically then it can control your ACs or heaters so that the living environment is very comfortable. Also, there are these smart plugs. So these are at plug level. You can measure the energy consumed by refrigerators, washing machines, different appliances that are present in your house. And also you have these smart fridges, which can actually maintain a grocery list of items that you may need to buy. The current smart fridges are not necessarily that smart. You have to enter all that information. Essentially, it's a tablet on a refrigerator. But in the future, it is anticipated that they can actually detect food spoilage through some sensors, because when food spoils, they release some kind of ammonia or some gas at a very minor level. Maybe those sensors will be installed in the future. They can possibly look at expiry date of your food and send you an alarm that possibly you need to get fresh milk because the milk is going to get spoiled. And also there is something called as a smart lock. So essentially you can open your door with the help of an app. And increasingly, all these smart devices are controlled through phone or voice interface. I don't need to go into detail of these things. You know that there is Alexa, Siri app in most of the iPhones. Now, let me go into another application domain, that is smart transportation. In front of your screen, there is this picture of reactive lights being installed. So based on the proximity of a car which might be going on this road, the sensors on the road can detect the motion of the car and automatically turn on the lights. So this can result in saving a lot of energy. Instead of having street lights that are always on, with this system you can actually save a lot of energy. Also, you can have dynamic lanes. So imagine instead of a physical line which separates one lane to the other, there are these lighting lanes which can possibly, if there is any repair activity happening on the road, these can lead travelers to go take the right path. Similarly, road condition can be monitored, and there can be traffic management solutions. So in the city of Austin, they have installed around 170 Bluetooth beacons, and every time a road crosses that cross section, your MAC ID is essentially noted in their databases, and when you again cross some another cross section, they can actually calculate the amount of time you took to travel between these 2 points. So you don't have to have monitor each and every car. If you can just monitor few cars which have their Bluetooth devices on, they can essentially make a good estimate of amount of traffic that's on the roads, and they can dynamically change the traffic lights to make sure that there is no congestion in our roads, and this is already happening. Yeah.
How can you track the MAC addresses of the Bluetooth devices that have paired with each other?
So these are not paired. If it notices that there is a Bluetooth device that is on, even then the MAC IDs can be registered. You don't need to pair essentially. You need to pair to transfer data or send some kind of signal, okay, turn on my headphone or something like that.
But isn't this an invasion of privacy?
Oh yeah, so the whole lecture today is about invasion of privacy, and I'll possibly not venture into that because I am not the right person to answer these questions. I have not really worked on privacy as such, but you're dead right. All these sensors that are part of our lives, there needs to be a discussion, I mean, not just among computer scientists, but also the policymakers, governments, and also individuals to decide how much they want to share and how much they are comfortable with. So I'm very sure the city of Austin didn't take a poll saying that, okay, should we install these Bluetooth sensors everywhere? But yeah, it's a very tricky question actually. It's part of it is a computer science problem to set up right policies so that users have access to their data. Part of it is the soft side of things. You need more discussion on it. You probably involve some social scientists to answer that question. Yes, so connected cars is another cool application. So apart from the basic use case of accident avoidance through detecting pedestrians, so one bus can say that, okay, there is a pedestrian walking, and it can inform some another car which is behind it, but that car may not directly see the pedestrian. So those are the use cases where connected cars will come into picture. And this has implications in fleet management. So there are lots of trucks carrying cargo all across the country, all over the world in fact. And imagine these trucks communicating with each other, their speed, their traffic condition. So they can actually travel much closer to each other because it's safer. They can be controlled, possibly even the brakes can be controlled by these sensors. And that can save a lot of energy in terms of, you would have seen in every traffic signal. So the first car moves and the last car takes some time to move. With the connected car, all the cars can start at the same time rather than the delay getting propagated. All the cars will start at the same time or stop at the same time. And of course, even connected cars can be used in real-time public transport alerts. Now, I mean, we have seen a lot of cool application domains, but how would one go about building a smart device? And I have taken a couple of examples out here. So for example, my favorite example in this lecture is a Fitbit. So a personal device, how would it communicate with the cloud? So initially, you have your smartphone. You want to sync all the data that is recorded in your watch to somewhere in the cloud, which will do all the analysis and give you feedback. So there are 2 steps to it. First, you sync your smartwatch with a mobile phone, and you will transfer data through Bluetooth. And then this phone essentially acts as a gateway to transmit this data to the cloud, which can perform all sort of analysis in terms of, okay, your heart rate is this, so your sleep pattern is this, and that information is downloaded by your phone, which you can see, the results can be seen in your smartphone after that. Not to mention there is, of course, significant privacy implications even in this one. Another application is some kind of a plug meter recording energy information of different appliances in the house. that can either directly send data to the cloud or it can send data through some router. And then you will get a cool dashboard, and you can see that, okay, you are using a lot more air conditioning these days, or in fact, it's still winter, I assume, so heater. So I've discussed these couple of apps, but how to, if you want to go about building such apps, you have to know the actual sensor platform, right? So let's briefly discuss the sensor platform that we are going to, how we'll go about building this big IoT deployments of smart transportation and all. So most of the smart devices are essentially sensor nodes, and they also have some computing capability, but these are resource constrained distributed systems, so you cannot perform all the computations on your smartphone or a sensor. So the data has to be sent somewhere for further computation, making sense of the data that you have collected. So in a typical sensor platform, it's made up of small CPUs, and they can be really tiny microcontrollers, such as an 8-bit instruction set with just 4K memory. And there are reasons for such a small, such a minute microcontrollers being used in IoT deployments, which I'll briefly discuss later. Also for communication, they might use some kind of radio communication, such as Bluetooth, Zigbee, and the transfer rates are around 10 to 200 kilobits per second. And of course, there are sensors, and these sensors are driven by battery or self-powered through some vibrations. And because of this restriction, you need to go for small CPUs that consume very small amount of energy. You cannot have a full Linux box doing a little bit of sensing and then consuming a lot of energy. And of course, it will have some form of storage. Now, a couple of examples of small CPUs. For example, this is still a very popular microcontroller which is used in IoT deployments called Atmel AVR. Are you guys aware of Arduino? Yeah. So Arduino, at least the early versions of Arduino used Atmel AVR. I think the current version uses some kind of an ARM processor. So it's an 8-bit instruction set, just 4 kilobytes of memory, and so the storage is actually on chip in a single board, and it consumes around 8 milliamps of energy. Another example is from Texas Instruments, which is called MSP 430, and this is another microcontroller which has a 16-bit instruction set, slightly higher memory. The flash is around 48 kb, but the power consumption is much lower, around 2 milliamps. And this trend you will see in computing, not just in terms of looking at small microcontrollers, but even modern machines. Over the past several decades, Moore's law says that the amount of transistors that can be packed in a given area is going to exponentially increase. I'll not say the amount of computation has become cheaper in that exponential rate, but it has continuously dropped. And so this trend of using less energy for doing more compute can also be seen in normal CPUs. Also, for doing some larger sensor beds, you would need much more powerful processors. So there is this ARM series, and I mean, these are again much more weaker compared to the ARM processors that are there in your mobile phones, or even in a small computer like a Raspberry Pi, which has, I think, ARM Cortex CPU. So it's much more powerful. It has a clock speed of around 1.4 gigahertz. So this one is much slower. Now, you have all this computing capability, but when you talk about IoT, it's about networked physical devices. So you need to communicate whatever information that you have with you, right? So how do you go about communicating this information? So that's where you use low-powered radios. I'm not sure if you have heard about ISM bands. So ISM stands for Industrial, Scientific, and Medical Band. So each and every country in the world sells bandwidth as a national resource. So for example, 3G, 4G communication requires some spectrum. So most of the countries sell this spectrum to different cellular providers. Similarly, different part of the radio spectrum are licensed. The band that I'm talking about here is actually unlicensed. So any one of us can design our own DIY project which uses this bandwidth range, and we are free to use this we are free to use this bandwidth without paying the government or any other entity in the world. So these are part of unlicensed range in radio communication. So this is a very popular frequency in ham radio sets in some countries. That's 900 megahertz or 33 centimeter wavelength, and 2400 megahertz. That's the range in which Bluetooth operates. So, and take these numbers with a pinch of salt. Like Bluetooth doesn't operate at one frequency. So Bluetooth technology uses frequency modulation. And just to refresh a bit of your signal processing that you might have learned in your undergrad days. So information is communicated between two devices when they use radio through some kind of modulation. By modulation, I mean, it's a very complicated word of saying change. So in case of Bluetooth, it uses a fancy frequency modulation technique where the range of 2400 megahertz to around 2485 megahertz are used, and at certain frequency it shifts from one frequency to the other. So if you want to convey information from sender A to sender B, you will actually continuously change the frequency level. And this change in frequency level is actually noted by B, which knows exactly how to interpret this change in frequency. And that information can be converted into bits for communication. Another popular modulation technique which is used by Zigbee, which is another open standard of communicating in low power radios, is modulating phase. So any electromagnetic signal, we always see this sine wave in all our textbooks. Frequency is essentially to do with the length of the signal. Phase is something to do with the point at which the two signals are out of phase or in phase. So you can actually change the phase and again communicate information. Of course, even in this case, B has to know the method in which you are transmitting data, and of course, again, this phase modulation can also be used to communicate information. And most of these like protocols have a very short range. Bluetooth 4.0 has a range of around 100 meters. The new Bluetooth that's 5.0 is expected to have a much higher range of around 400 meters to 1 kilometer. But of course, these are all theoretical numbers. And I don't have to tell you that nowhere, I mean, our Bluetooth devices have nowhere near this range because of interference, atmospheric interference buildings that we are surrounded with. And so there are these chipsets available for sending this information. For example, ChipCon CC2420 can be used to communicate the information from one sensor to the other. And so transmitting, it takes around 9 to 17 milliamps, and the receiving is around 19 milliamps. Now, here is a puzzle. Why should receiving information be more expensive in terms of energy than transmitting? One would assume that transmitting data would require more energy, right? Exactly. So when you transmit information, transmitting information can happen in milliseconds. So there is this big surge of energy usage, you transmit data, and then you just go down, that's it. Whereas in case of receiving, you don't know when the information will be received, so you have to be always on. So in terms of power consumption, transmitting is possibly 10 times higher than receiving, but in terms of energy consumption per unit time, receiving more often than not is more energy consuming than transmitting. So all these design considerations have to be in mind when designing an IoT deployment. You can have very high sampling rates, but that will ensure that your sensors are draining battery very quickly. As I mentioned, listening can take more energy than transmitting. Okay, so battery power is an extremely important factor to be considered while deploying an IoT system. It's okay to have like thousands of sensors spread across in your space, but each of these sensors need to be powered. So one way to power them is battery, and this picture is of a moat called Mica 2. So who among here knows what a moat is? No one? Well, again, this is a very fancy term. It's a very simple thing actually. So moats are essentially devices which help in sending signals from one part of the network to the other. So moats are often used in IoT deployments where you have like multiple sensor nodes, and many times the information that needs to be sent might be outside the range of the radio, low power radio technology that you're using, Bluetooth or Zigbee, whatever. So the actual receiver might be somewhere here, and this node out here cannot send the information directly. So more often than not, IoT deployments have multi-hop capability. So information from this sensor can reach the receiver in more than one hop. And also IoT deployments are quite dynamic, so any of these points can go down. So there is dynamism in routing as well. So even if this node goes down, it can use some another node to transmit the same information. So Mica is one such moat. So it essentially looks at transmitting data from one end to the other and any different direction. So, and these moats also have an operating system installed in them. So if you can Google after the class, Google TinyOS. It's a project from UC Berkeley, and they have designed operating system for such moats. So the battery capacity of a moat, that's Mica 2, is around 2,500 milliamp hours. So it can be powered by 2 AA size batteries, and the power consumption on average is around 25 milliamps. So if you do a simple math, you will run out of battery in 100 hours. So there are we need to leverage some techniques so that we can extend the battery life. So what are the alternatives? One alternative is a very dumb alternative, is to use a bigger battery, which is not always possible. Second thing is, don't use batteries. Harvest the energy that you're getting, or use a small battery which can be recharged. So you can have some tiny solar panels which are charging your batteries, or wind, motion, vibration. So there are multiple ways to harvest energy. And the third thing is duty cycling. Rather than being always on, as you mentioned, you can predict the nature in which you will get the data and possibly turn off for a few seconds, and maybe leverage the fact that your dynamic system is very resilient and maybe some failures are okay. So you don't have to listen all the time. So you can always do duty cycling. Of course, coming to the sensors, there is a plethora of sensors that are there. There are these weather sensors such as temperature, humidity. Very easy, they just measure temperature and humidity. All our mobile phones have magnetometers which tell you the direction of the north and the south, that is geographic north and south. And each one of us has used it. So whenever you turn on your maps, and you see that whenever you take a turn, the map automatically rotates to your vantage point. So that's because Google Maps is using the magnetometer to make sure that, okay, I need to change the orientation based on the direction in which you're moving, right? Similarly, one can use acoustics, light. So our mobile phones automatically brighten when there is more sunlight and, less sunlight, or the other way around. More sunlight, and when it's the ambient lighting conditions are a bit dull, then the brightness can be reduced. Again, another battery saving strategy. and also it helps looking at your mobile phones in a more clear light. And of course, there are accelerometers. So accelerometers can tell you what's the orientation of your mobile phone. So any object, may it be mobile or us, everyone is experiencing acceleration. That is acceleration due to gravity, which is pointing right towards the center of the earth. So by looking at the x, y, and z coordinates of the acceleration, you can actually tell what is the orientation of your phone. So one cool application is while gaming. So you want to know what angle your phone is, and that can tell you the precise angle in which your phone is facing. Another use case is it can act as a pedometer, that is step counting. So changes in acceleration give a very distinct signature of a person moving from point A to point B. Every step is actually a signature in the accelerometer readings. So there are many other sensors, and I'll not go in detail of each of them, but as you can see, there are many sensors, not just in built environments, but also in our mobile phones. Now coming to one of the key enablers of IoT deployments is self-harvesting sensors. So as I discussed earlier, one can harvest energy from the environment to power these sensors through tiny solar panels, vibrations. They can use thermal power, airflow, and wireless energy. So there are like a lot of cool papers that you can read, and it can enable large-scale IoT deployments. Okay, so what are the typical design issues that you would face while designing an IoT system? So let's look at different levels. So for example, you have this sensor network. Each of them is communicating with the other sensor. And let's look at just a single sensor for the time being. One key issue is how to do power management, how to harvest energy to maximize the lifetime, how to do duty cycling. So that is one design issue that one needs to focus on. The next is to look at the network, the whole network. And one thing is, how do you combine the data from different sources? How do you make sense of a temperature sensor and humidity sensor and make sure that you combine? They might be sending data at different sampling rates. So all that computation aspect has to be looked at. As I mentioned, duty cycling and localization, essentially node localization and time synchronization is one of the most important problems in wireless sensor networks and IoT deployments. So for example, when you get a signal of say some distress, so you want to know from which part of the network you are getting the signal. So there are various techniques such as signal strength, direction in which you are getting the signal, so that you can localize on the actual sensor that is sending this information. And another problem is routing. So as I mentioned earlier, wireless sensor networks are highly dynamic, but they are also resilient. So they need to make sure that information is sent from one node to the other, and they need to be capable of building ad hoc networks and sending information. And once the data is sent from the sensor networks to the cloud, now there are many other computational challenges. So for example, on the server side, that is once the data leaves the sensor network, how can you perform big data analytics on this data? How can you derive insights from this data that you get? And also make recommendation and send alerts to the user of how to change things. And maybe also actively control. Once you know what decision to take, you can actually turn on an air conditioner or turn on some sensor on your phone. So there are many things that can be enabled. Now let's change gears and pivot towards a topic which is very close to my research called green computing. And green computing has seen massive IoT deployments in physical environments over the past few years. And basically, green computing entails two aspects. The first aspect is greening of computing. that is sustainable IT. How do you design energy efficient hardware, software, and systems? And the second thing is computing for greening, that is use of IT to make physical infrastructure more efficient. For example, our homes, offices, buildings, transportation. Okay. So there are two key aspects, and we'll go into the detail of these two aspects. Until now, are there any questions on the aspects that we discussed before? Yeah.
So when you want to construct a device with certain number of sensors,
Right.
how do you assess what kind of battery power would you need, what kind of other resources would you need?
So it totally depends on the sensor that you are using, how easy it is to replace the battery. So if you are monitoring, so there are projects which are where UMass is involved, where we go into forests to record sounds from different animals. So you cannot go there every day to replace a battery. So it's all dictated by the physical constraints that you have. And of course, there is a trade-off. So if you can't go to that place, can you harvest energy? Or can you duty cycle your sensors so that you don't waste a lot of energy in very small amount of time? So all those design decisions come into picture. And also, you can do sensor fusing. So for example, some sensors consume more energy than the other. So can we use combination of sensors to derive information about some other thing, right? So you don't have to have a GPS sensor possibly. You might do with some other kind of motion sensors to detect any motion of some animals in a forest environment. So there are tons of research there are multiple ways to solve the problem that you are discussing essentially, right? Yeah.
So when there are multiple devices interconnected, how do they actually communicate? What type of signals do they use?
Oh, so there are several communication. So I just discussed two of them. Like Bluetooth is one open standard to communicate information from one device to the other. There is Zigbee. So all these open standards have their own limitations in terms of the bit rate in which they can send information, the energy that they consume, and how reliable they are. So again, it's as with any design problem, you cannot say in advance which one protocol is the best or one frequency modulation is better than phase modulation. It all depends on the application that you're involved in. So there's no one clear winner, essentially.
With regards to the microprocessor that handles these different types of sensors, is there like a unified microprocessor that is used for like sensor?
Not really. So for example, in research, many times if you are not involved in building the sensors yourself, you are interested more in the data, then you'll go for very reliable computing sources such as Raspberry Pi, right? That consumes a lot of energy. But you are not interested in solving the problem of deploying it for a longer time. But if you are working in sensors, you are actually deploying it in the ground. You work with different constraints. So possibly then you'll go for more low power sensors, low power communication. Can there be a way in which I can have a receiver which is doing some local computation and then sending compressed data to the cloud? So there are many ways in which you can design a system. Yeah. Hi.
We're talking about how like society is changing as a result of these things. I guess it's also philosophical. For instance, if you have a sensor in the forest and a tree falls, but you're not around, does it make a sound?
So, as I mentioned earlier, most of these wireless sensor networks are designed to be very dynamic. So, there is a whole field of research called sensor placement, which looks at the problem that you have asked out here, how to optimally place sensors in such a way that with minimum number of sensors you can get most information. Also, where to place exactly so that there is redundancy. So for example, one sensor has a range of let's use this space. So I'm just trying a hexagon out here which shows the range of that sensor. So rather than packing them in this fashion, like close to each other, no overlap, you can pack them slightly closer so that there is some overlap. So even if there is some sensor that is going down, you place them in such a way that probabilistically you will get a good coverage of whatever data that you have. Yeah. So I mean, again, sensor placement is a very old problem, much older than probably I am, and the problems are still active. I mean, it's not to say that the problem is solved. For different kind of problem setup, you might have different constraints, so you need to solve some different kind of optimization problems to actually get the perfect sensor placement. Yeah. Okay, so moving on. Okay, so I talked about green computing, that is greening of computing, that is how to make sure that all the compute that's happening is using the least amount of power, how to make sure that your data centers are consuming less energy as more and more computation is offloaded to them. And the second thing is how to use computing for greening, in the sense how to make our built environments like this building more energy efficient by installing more sensors, keeping track of your energy use, and providing active feedback to the user. So let's start with some brief historical overview. So again, this is not a new problem. So mobile devices have a long-standing problem of how to conserve battery, because we obviously don't want to charge our mobile phones every 2-3 hours, right? So there are a lot of policies that are already part of our mobile phone, in the sense how to turn off the screen, when to make sure that the screen is on when the phone is close to a user. So there are a lot of policies which make sure that the battery in our mobile phone is conserved. Now, there is a recent growth in data centers where big companies like Google, Apple, all these companies, and in fact even other non-IT companies use data centers to store their energy, record their transactions. And a typical data center might have hundreds of thousands of servers. So the actual cost of computing is a significant portion of the expenses that you experience as a company. So obviously you want to reduce that cost, right? So the key motivation here is to reduce your electricity bills, not necessarily to save the planet or something like that. And of course, how to apply greening to other systems. As I said, how can you monitor this building and make sure that, okay, there is always a heater on in this particular room at this time where nobody's there around. So all these insights can be produced by monitoring the built environments. Okay, so let's look at computing and the power consumption associated with like modern buildings. So in office buildings, 20% of the power is consumed, like of all the energy that's consumed in the world, 20% goes in office buildings. In a college like UMass, 50 to 80% of the energy is going in computing resources. For example, STEM fields are becoming increasingly more data-driven. They run their compute on like large clusters. They are contributing to it. And data centers are currently contributing 3% of carbon footprint, and they are growing. We all have read stories that, okay, Google is installing this new big data center in Iceland to save energy, and it's going to have zillions of servers. So all these companies are increasing their infrastructure. So as I said, like data centers are a large fraction of the IT carbon footprint of the world. And obviously PCs, desktop, and even mobile phones are a significant part. Okay, so what exactly is a data center? I think all of you know this very well. So this is essentially a facility of housing large number of servers. So they can have network storage and other things. And let's take an example of a Google data center in Dales, Oregon. So the size of this data center is actually 12 times the size of a normal football field. It's housed in a massive complex. It has 100,000 servers, and the power consumption at its peak capacity is around 100 megawatts of energy. So that's enough to power a small city. Now, obviously, Google doesn't want to spend that much energy. They want to make sure that you save money and improve your operations. So this is an important problem, and they are heavily interested in this one. Okay, so before going into the scale of 100,000 servers, let's look at the cost of one server in a data center. So in this graph, the blue line actually shows the cost of a server, that is cost of buying a server, considering a server life is 3 years. So they have assumed a high-end server of $4,000, and IU is essentially a unit of rack size. So IU means 1.75 inches. So a server of that size, which will fill that much space in a rack in a data center. And as you notice, the cost of the server has not necessarily increased or decreased with time. So that's an immediate observation. But there are two other costs involved here. One is the energy consumed by these servers, which is increasing with the energy costs are going up, so the energy bill of the servers will also go up. And the second cost is the infrastructure cost, that is to cool the infrastructure. So all these data centers have massive cooling needs. The heat has to be taken out of these data centers, so a lot of energy is used in maintaining the temperatures of the data centers. So all this cost is actually higher than the cost of the server itself, which is not ideal. Now, we can focus on the Google data center that we discussed earlier, and let's see what's the energy cost involved in this data center. So as I mentioned, there are 100,000 servers. Monthly cost of one server is around, say, 500. The power consumption is 500 watts. So if you want to calculate the monthly energy cost, it's around $50. Now multiply that by 100,000 servers. If they are always on, the number comes to $5 million. And what's the cost of cooling then? So people in the industry who work with data centers use this term called PUE, that is the power usage efficiency. So power usage efficiency is nothing but the total energy cost divided by the server energy cost. So if cooling requires $5 million and the monthly bill of running a server is $5 million, then the PUE is around 2. That is server cost plus cooling cost divided by the server cost. But Google data centers are pretty efficient. They have designed their complexes in such a way that the heat is taken out quickly. They have housed their data centers in colder climates, so you get free air from outside, free cold air from outside. So the Google PUE is around 1.2. That is, the cooling cost is 20% of running the server cost. It's just a number that we need to consider. It's highly efficient data center. Now, designing an efficient data center involves following things like reducing the cost of running the servers, cutting cooling cost, employ green best practices. Now, let's look at each one of them. So reducing server cost can be done in different ways. One thing is to employ better hardware. Newer and more efficient CPUs are entering market at an increasing rate. So the cost involved, the computations per watt is improving. So newer machines obviously would spend less amount of energy. There are better power supplies, more efficient power supplies, which convert the AC power into DC to power all your machines. So you can go for a better power supply. And this is non-intuitive. So you can actually use DC power, and it can be more efficient than and AC power. So from power electronics literature, we know that AC power can be transmitted for long distances without loss. But the same cannot be true in case of data centers, because there are a lot of conversions happening from solar panels producing that power to step down transformers. There's a lot of energy conversions that is happening all along the line. So one line of research talks about directly using DC power. So that apparently can save energy. And you can obviously manage your servers better, intelligent power management policies, turn off servers when not in use. And of course, you can pack many applications that are running on different servers into one server through virtualization. So instead of 10 different servers running applications which are not having high utilization, you can combine them and house it in the same machine. And through virtualization, you can actually fool the app by saying that, okay, it has its own dedicated resources like memory, CPU cycles, etc. Cooling, reducing cooling costs. So one thing is doing better thermal engineering, better airflow. I think mechanical engineers are better suited to do that. And of course, move to cooler regions, as I said, so you get free air from outside, which is cool. And of course, you can naturally cool the data centers. And there is also another data center in Switzerland which uses geothermal energy for cooling. So they use subterranean cold water to actually cool the data center. So again, some innovative techniques which can be used. And one solution is, of course, to build data center in Iceland. So there are many other considerations. So you may not always want this, because some applications are latency sensitive. So you don't want to experience the latency of pinging a server in Iceland and then back. So may not be always possible for all applications, but for some applications, obviously a promising solution. Now, there are other strategies to reduce power consumption in corporations. That is through desktop management. So large companies have, say, around 50K desktops. If they're always on, and many times IT tasks such as backup, security, virus scanning happens in the night. So you need to keep your desktops on throughout the day. Not ideal. Now, there can be better desktop policies such as automatic sleep policies. And there was this work done in Usenet conference in 2010, where they make sure that there is a policy which ensures that there is easy wake up and user doesn't experience any distress, in the sense some security patch not being installed. So they make automatic wake ups, easy wake ups possible, so that you don't miss any security wake ups, security patches, but at the same time you conserve energy. Now let's focus towards IT for greening. How can we use these sensor networks that we have seen or heard about in this lecture to improve the management of a building? How to make it more green? So one can think of building as a distributed system. It has a building like this might have hundreds of thousands of sensors. They monitor energy, occupancy, temperature, and they analyze data in the sense, so there are these control strategies of when the lights should turn on when someone walks in. And also one can use renewable energy to reduce the carbon footprint. So we can look at IT for greening at different levels. One is to look at measurement and monitoring. So most of the residential buildings in US come with what's called as a smart meter, which records the energy of a whole house. Similarly, there are other measurement entities which measure different aspects of a building, and they have different application in terms of faster handling of outages. So through smart meters, the utility can know that, okay, this house is experiencing outage, send an engineer to fix it. Another aspect in which IT can bring greening is to provide analytics on the data that is generated in this stage. You can do forecasting of energy and make sure that the energy supply demand is maintained in a grid. Many countries experience blackouts because of this supply demand being not matched, and using IoT deployments can actually improve the condition significantly, and employing machine learning techniques to predict energy usage in the future. And obviously, finally, you also want to control things. So many washing machines are coming up with ways in which they can directly talk to the utilities, get the price of electricity at that point in time, and essentially delay their execution. So this particular technology is called demand response, where based on electricity prices, you shift your load, you shift your energy usage to non-peak hours of energy use. So in many countries, the cost of energy is actually dependent on the time of use. So these kind of strategies can actually elevate the problem of peak demand. Again, building monitoring I have already discussed can be done at different levels. This is a plug meter which records energy usage at an outlet level. E-gauge is an energy meter for a whole house. It's actually a full Linux box, and it can actually give you some cool dashboards to look at your energy consumption of your solar panels, your energy consumption, and of course there are smart meters that are installed all across US. Now, how do you go about analyzing the data? One is, so each building, actually each large building has something called as a building monitoring system, and this actually takes information from different sensors to control the HVAC at different parts of the building, recording the doing people counting. So most of the cameras that you see in the campus are employed with people counting sensors. So simple computer vision can be employed to see how many people are walking into the building, going out of the building. That can be insightful in controlling the HVAC. And of course, modeling, analytics, and prediction. So you can use machine learning techniques to answer several questions. One is, which house has inefficient furnaces, heaters, dryers? Or are you wasting a lot of energy in your house? And is an office building AC aligned with the occupancy pattern? And when will the aggregate load or transmission load peak? So these kind of prediction type questions can be answered by employing machine learning techniques. So a Nest thermostat will essentially look at a temperature, humidity sensor, and an occupancy sensor to label the data as the person being occupied or away from the house, and this being repeated over several days, one can automatically learn a schedule, a 7-day schedule for a person. So Nest is increasingly using more and more advanced techniques to come up with faster convergence to a set schedule. Similarly, it can identify any misalignment in AC usage. So for example, here there is an AC signature which is identified, and this misalignment can be used in the future to possibly shift the occupancy, make sure that the AC is never on when you are not in the house. Okay, so one way to handle or reducing our carbon footprint is by incorporating more renewables in our energy usage. There is significant growth in solar energy in US. In the last 6 years, the solar deployment has increased from 2.3 gigawatts to 40 gigawatts. In countries like China and India, in the last year, the solar deployments have doubled. So it's increasing all over the world. They can be in different forms like rooftop wind turbines, which are not necessarily popular all across the world, but everybody knows solar PV installations, and solar thermal for water heating. The problem with renewable energy is the intermittent nature. So photovoltaic panels are essentially nothing but PN junction diodes, and the problem with PN junction diode is they are sensitive to temperature. And with temperature, the resistance of the PN junction increases, reducing the efficiency of the solar panels. Another problem is obviously with cloud cover, dust, snow, the amount of photons that are falling on the panel itself is reducing. So because of all these dynamic factors, solar energy is not necessarily highly predictable. So in a very clear day, you will see this nice sinusoidal curve of energy that is generated using solar energy. And on an overcast day, you see something like this, very less power being generated. And on a scattered cloudy day, you see that there are large gyrations in the amount of energy that's generated. These 3 days actually happened in the same week of April. So it's not like there is a high weather correlation. This can happen every week, such variations. So one problem is forecasting the renewable energy so that you can use this insight and leverage solar energy when it's being generated. So one can use machine learning models and weather forecasts to actually predict energy from solar or wind turbines. And these forecasts can be used for near-term generation. And we can schedule some of the loads based on the solar energy being generated. So there are several use cases. One use case is to have an EV charging station. So in our university itself, we have these parking lots with solar panels mounted on them. Imagine a possible use case of offices or a car rental service like Zipcar. So in these places, you can actually make some assumptions about what will be the arrival or the departure rate of different electric vehicles, and you can leverage some accurate solar prediction. And based on these arrival departure rates, one can have a very intelligent scheduling policy. So for example, when you know the arrival departure of electric vehicles, this problem essentially translates to scheduling in a preemptive uniprocessor system. And the most optimal solution there is earliest deadline first. So as is the case with the jobs coming to a processor, if you know the arrival and departure timings of a job, or in case of jobs, you know the amount of resources that need to be dedicated when it needs to be completed, you can actually schedule them in an optimal way. Of course, not all these assumptions can be possible in a real system. So maybe with different set of assumptions, you come up with a different algorithm, not the earliest deadline first. And of course, these questions like when to charge, which EV to charge, and how much to charge are not so straightforward. So imagine a case where there are 2 electric vehicles. So EV1 and EV2. So EV1 has 90% battery charged, and EV2 has 10% battery charge. So obviously in this case, and if you have say X amount of energy, a fair strategy would be to just give X by 2 to this one, this EV, and X by 2 to this one. But it may not be fair because this one already has 90% charge, so possibly you can give everything to EV2. So I mean, this is a very simple scenario of just 2 EVs, the contention between just 2 EVs. But when we talk about dynamic arrival departure timings and different assumptions or constraints in your system, designing a scheduling policy is extremely hard. And in many cases, in fact, most of the scheduling problems in this world are NP complete. So you need to come up with some kind of an approximation strategy to solve this problem. And obviously, the most important challenge is to involve people in decision making, in the sense provide some kind of incentives to reduce the energy usage. One way of doing it is to have immersive apps, provide a game in which you say that, okay, reduce your thermostat set point by 1 degree and you will get some green points. Such experiments have been done in the past and have proved to improve and have resulted in improved energy efficiency or reduction in energy usage. And of course, you can provide personalized feedback about your energy usage. You can say that, okay, the thermal usage in your house is higher, so possibly you can take some steps to improve that. and maybe you can direct some rebates from governments, in the sense if you know from this analysis that there are a lot of inefficient appliances, government actually provides rebates for certain kind of replacing certain kind of inefficient appliances, so you can direct them to that. Well, in summary, this work, so greening of computing essentially involves using better processor, better building environments which use less cooling for your data centers, having better software which can reduce the energy usage, and of course, computing for greening is how to make use of IT, big data to reduce the energy footprint of our buildings through monitoring, analytics, and control. And of course, you can use intelligent software or mechanisms for power management. And forecasting of renewable energy obviously can improve the integration of renewables in our energy mix. Well, that's it from my side. If you have any questions, we can discuss. Any questions? Okay, so thank you. And if you have any questions, you can contact me offline. My email address is Srini, that is SRINI @cs.umass.edu. So if you have any questions about the research that we are pursuing, or if you have any interest in using some of the cool data sets that we have collected, you can just shoot me a mail. Thank you. Thanks. Yeah. Stop recording.